Welcome, pre-calc honor students, to Chapter 2, where we review a lot of the ideas from polynomials and extend some of our skills. The following are examples of polynomials. Does this list look good? Are all these polynomials? Well, let's look at what the definition of a polynomial is. Many terms, from the two ideas, polynomial. Each term has a non-negative integer as the power of the unknown. So let's go back over a list and see which one of those we'd have to get rid of. Clearly, this does not work because it's a 1/2 power. It must be an integer power of x. This is a rational power. It's not an integer power. How about 3 over x? That's x to the negative 1. That's negative. So that's no good. How about 42? 42 is okay. It's x, 42 times x to the 0. So we accept that as a polynomial. It's called a monomial. Now, polynomials have many terms. That 42 we just talked about is a constant term. It's x to the 0 power. If it's just got a degree of 1, like 31x plus 7, that's linear. And 7 minus x squared, we just talked about those as quadratic. Cubic if 3rd degree, quartic if you have 4th degree, quintic if you have 5th degree. Now, let's talk about how we work with polynomial functions. Find p of 3 by direct substitution. This is a straightforward approach, and sometimes it's faster, especially if you just have a few terms to look at. You put 3 in wherever you see an x, grind through it, and you get 14. Let's see if we can do this actually more easily with synthetic substitution. Here goes. We put a 3 in the box, 3 in the box, and we start by bringing the first coefficient down, then always multiplying by the number in the box. So you get 6 here, and then add in the columns, 1. Multiply by the number in the box, and then add, you get 6. Multiply by the number in the box, it's 18, and add, you get 14. And notice, iguales, they are the same. Okay, synthetic substitution much faster, mainly because you don't have to do all these powers in addition to all the multiplications. You've simplified it just to a series of multiplications and additions. Let's see why this works. It looks like magic, but let's go through this synthetically now. We bring the a down, multiply by the number in the box, that's ax. So this is ax plus b, multiply by the number in the box, so it's ax squared plus bx. Add them up, adding in the columns, right? Ax squared plus bx plus c, multiply by the number of the box, times x. So you get ax cubed plus bx squared plus cx. And then finally add, and you get ax cubed plus bx squared plus cx plus d. So that's how it works. How synthetic substitution works. Now, synthetic division is a faster way to do longhand division, but you have to have certain terms. So if I'm dividing this, let's review longhand division first. If I'm dividing by this, it can be a bit of a chore. Which we get from x to x cubed, we have to multiply by x squared. So I'm going to put the x squared in this column, and then actually multiply both these by x squared. So that's x cubed plus 2x squared. And here's the painful part. Now you have to subtract. Use a different colored pen here. Just say we're subtracting off this quantity. So you actually get the x cubed falling out, but this is negative 3 minus 2, so you get negative 5x squared. Now we bring down the next 2x. Now let's look at our next one. To get from x to negative 5x squared, we did negative 5x. Now multiply both those by it, negative 5x squared plus negative 10x. When you subtract, these fall out again, and you actually get a 12x here, because it's 2x minus a minus 10x. Bring down the 5, and now we'll finish up with a 12 plus 12 to make 12x plus 24. And you see we have a remainder of 24. Now let's see how much easier this is with synthetic division. When we divide by x plus 2, we actually put a negative 2 in the box. That's because we have to think of this as x minus a minus 2. It is what you subtract from x. That goes into that box. Then the coefficients, 1, negative 3, 2, 5. Let's go through this. Bring down, just like synthetic substitution, but we're getting so much more out of this. Watch what happens. Multiply by negative 2, and we get negative 2. Add negative 5. Multiply by negative 2, you get 10. Add 12. Multiply by negative 2, you get negative 24. Add negative 19. And we realize that this was an error, because I forgot we were subtracting cell quantity, so yes, you do get a negative 19 here. The answer here then is normally written out as x squared minus 5x plus 12 plus negative 19 over the divisor. Notice that's the same thing we had here. You have to untranslate this. This used to mean 1x cubed, but now that you've divided out an x, it only means 1x squared. So x squared minus 5x plus 12, and then the remainder is put over the original divisor, x plus 2. See how much easier synthetic division is. Now the remainder theorem is when a polynomial, p of x, divided by x minus a, the remainder is p of a. This is the claim. Let's check that by going through a proof here. If you take p of x and divide by x minus a, you'll get some other polynomial, which is called q of x for quotient, plus some remainder over x minus a, where that's the remainder, right? And here's our original polynomial. Now, if we multiply through by an LCD of x minus a, we'll end up with p of x equal q of x times x minus a plus r. And when you substitute an a, put a in for x, p of a equals q of a times a minus a plus r. Well, this is 0. So there you go. P of a equals the remainder. And it's an amazing result. And so when you're asked questions about how to find a value of a function, you can go through synthetic division and just look at the bottom right-hand corner. Now the factor theorem is just an extension of the remainder theorem. Remember from the remainder theorem, we have that p of a is equal to r, right? Well, if x minus a is a factor, that means x equals a is a root. If you got a factor or root, the remainder should be 0, so therefore p of a will equal 0. There's no remainder, because x minus a factors in exactly. And that's what we're looking for when we start working on polynomials. I'm trying to solve this polynomial equation, and I want to find the other two roots. I'm given two of the roots, 1 and 4. First, we verify that those are indeed roots by going through synthetic substitution. Bring down the 1, multiply by 1, add, multiply by 1, add, multiply by 1, add, multiply by 1, add 0. There you go. By the remainder theorem, this says that x minus 1 is a factor. That can help us factor this out. Further, this is called the depressed equation. And there's a very key concept here. When you get a remainder of 0, you have to depress the equation. It's called depressed equation because the power has been reduced. In general, when people lose power, they get depressed. as do equations. So this is depressed, and you've got to learn to use the depressed equation and put the other root into it, the 4, and continue to work off this. 1 times 4 is 4, negative 3 and 4 is 1, 4, negative 1, negative 4 is 0. And so now we have another. Let's call it the doubly depressed equation. Doubly depressed equation. Kind of like when you lose your license and you're grounded. Okay? So make good decisions. Hope you did this weekend, kids. Here we go. Here's the doubly depressed equation. We're not given any more roots, but now we can translate this, what this is. This started out as x to the 4th. When we divide here, this came down to x cubed. Now it's down to x squared. It's x squared plus x minus 1 equals 0. And we can just solve that with a quadratic formula. Negative 1 plus or minus the square root of b squared, which is 1, minus 4ac, which is plus 4, over 2 times a. So we get our other two roots, negative 1 plus or minus the square root of 5 over 2. Here are your other two roots. Flange out.